Welcome to Chapter 5, the Electrical Electronics Classroom Manual. We're basically going to cover in this 1 week what the Electric 1 and Electric 2 classes cover in 16 weeks. So we're going to touch a little bit on a lot of topics. You can go back and review the classroom book on the Cengage website. There's also some extra activities in there that I've not assigned that wouldn't hurt to do if you really wanted to try and get more knowledge. But this PowerPoint will basically give you an introduction to the topics that we need to get out of this introduction to electrical and electronic systems. Basically, electrical and electronic systems refer to two different things. Electrical and electrical systems refer to the wiring and electrical parts. Typically, this involves mechanical devices that move. When I'm in the classroom, I'll give a demonstration and typically flip the light switch on and off. By mechanically moving the light switch, I've moved the electrical device. Electronics include computers and other black spot types items used to control engine and vehicle systems. They include many semiconductors. They are electronic. There's nothing mechanical. Diodes, transistors, and integrated circuits are all electronic devices that use semiconductors to do the work of an electrical mechanical switch. And the example is flipping the light switch on and off or clapping the clapper to turn the lights on and off. When you do the clapper, there's no mechanical device being touched. It's simply the vibration of the sound waves controlling the electronic devices that are attached to the switch. So that's one of the ways I try and explain electrical and electronics and the difference between them. Basic electricity is simply the flow of electrons from one atom to another. This illustration shows a bunch of little green circles with a negative sign flowing from one atom to another, to another, to another. And then that is the flow of electricity. The movement of those electrons creates the electricity. This is a little illustration that basically shows how to do an atom in motion. All atoms are in motion, even steel atoms are in motion, just very slow. But you see the one atom on the outside ring, the one element of that atom is an electron, and that's what moves from one atom to the other. The protons and the neutrons are in the center, in the nucleus of the atom. But that's where we get electricity from, is where this one atom on the outside ring here moves to the next atom. When we measure electricity, there's some terms that we use. Amperage is a term to describe the movement or flow of electrons. So basically, that illustration we just saw with the electrons moving from one atom to another is an illustration of amperage. Voltage is another term that we use to measure electricity. And this is the electrical pressure or potential forcing those electrons to move. And it can be measured. This little illustration shows the little man pushing against the electrons in that conductor. So he's creating voltage pressure, electrical pressure. Amperage, or amps, is a unit for measuring the electrical currents, the movement of electrons. It's measured by an instrument called an ammeter. And there's a very specific procedure for taking and doing an ammeter test to measure amps or current. We refer to this current as the movement of electrons flowing between the ends of the circuit. Voltage. Voltage, the unit of measure for voltage is volt. It's measured by an instrument called a voltmeter. Electrons are pushed or moved by voltage. Voltage is a measure of an electromotive force. You may have heard about this on Star Trek, but it does exist. Electromotive force, EMF. Now I've highlighted in yellow here, there's two theories of electricity, and they're basically the opposite. One says electrons move from negative to positive. The other says that electrons move from positive to negative. And typically in automotive, because our cars today are typically negative grounded, we talk about a conventional theory of electricity that moves from positive to negative. but basically there's no proof of either. If any of you ever watched The Big Bang Theory, this is the type of thing that Sheldon used to get into. So there's no definitive answer which way electrons actually move, but for our purposes in automotive, we use the conventional theory. Resistance is the third term that we use when we talk about electricity. Resistance is measured in ohms. It's measured by an instrument called an ohm meter. Resistance occurs when electrons resist being moved out of their shells. That one lone electron doesn't want to leave its home atom, kind of like you guys in the morning when you get up and have to go to in-person classes. Resistance to current flow does produce heat. This is why you may periodically see a car barbecue on the side of the freeway in the morning. If we don't wire our vehicles properly, they can actually create enough heat in the wiring circuits to start the car on fire. Only way to effectively use electricity is to have defined resistance, and we will find out how you engineer that into the vehicles. Loads are devices engineered to use resistance. Loads are things like motors or bulbs. Corrosion can also cause resistance. Some of the people back east where there's a lot of corrosion on the roads with the salt and the other chemicals can have a lot more issues with corrosion in their wiring systems. Unintentional resistance in a circuit can disrupt circuit operation. There are two types of electrical flow or electrical current. There's DC, which is direct current, and this is where the electrons flow in one direction only. This is typically we find in automotives. It must be connected positive to positive and negative to negative, like a battery. This would be a typical direct current. Alternating current, the electrons change direction at a fixed rate, frequency. It's found in homes and buildings. Typically can be connected in any direction. If you go plug a lamp in at the house, at home, into the wall outlet, you can plug it in either way. There's typically no directional requirement when we use AC current. When we talk about electricity and flow of electricity, there's two things to consider. Conductors are materials that carry electric current. This allows electrons to flow freely. One of the best conductors is copper. Such things as copper, silver are very good conductors. Insulators are non-conductive materials. These inhibit the flow of electrons. Rubber, wood, these type of things do not let electrons flow. Interesting side note here that I just point out at this time is when we talk about electricity, there's also a topic of magnetism comes up. Magnetism is created anytime an electric current is flowing. Magnetic field strength is affected by the conductor's windings and the separation of the windings from each other. Magnetic fields can be used to create electricity. Magnetic fields can also be used to perform mechanical work. You can consider that magnetism can create electricity, and that's where we take and turn the alternator and it creates electricity. Electricity can be used to create magnetism, which is what creates the force used by the starter to start the car. That's why some of the hybrid vehicles today use one device that can be either an alternator or a generator, a starter that they can use to charge batteries or to turn the car and make it go. It's all depending on how the electricity is controlled. At this point, we are going to bring up one of the common topics in electricity, Ohm's law, created by George Simon Ohm. Basically, he determined that 1 volt is required to push 1 ampere of current through 1 ohm of resistance. He did this through many years of practical application and experimentation. Volt is a standard measure of electricity, amp is a standard measurement of moving electrons, and ohms is a standard measurement of resistance. We've talked about these already. Ohm's law provides a basis for automotive engineers to create the systems in the cars today. By knowing what to do, they can create how things should work. Ohm's law is what the engineers use to create the systems to make everything work as smoothly as it does. Basically, Ohm's law is the basis for electrical system diagnostics. Based on what Ohm's law says things should do, we can go back and figure out what's not doing what it's supposed to. But there is a distinction. Ohm's law does not fix cars. Technicians do. Through the use of Ohm's law in their diagnostic procedures, they're able to fix cars based on what they've learned from Ohm's law. Basically, this is a little illustration of Ohm's law. It can calculate whether a circuit is operating properly. The three items, voltage, amperage, and ohms, are the elements of Ohm's law. These are a couple instances where we can use different things to try and find out what's going on. If we're trying to find out what resistance is, we can use the voltage and the amperage to determine that. Essentially, what Ohm's law tells us, there are three elements in every automotive electronic circuit, and one of those is out. That implies that there must not be another one out. So if we have a fault, a blower motor doesn't work at the proper speeds on the air conditioning of the car, that tells me there's one of two things going on. Either the resistance is increased or the voltage is decreased, because in that case, amperage is current in a constant. So by using Ohm's law and applying it what we've learned, we can tell when one thing changes, something else has got to change. So typically, if a customer comes in with a complaint, that's something that's changed. We can use Ohm's law to go back and figure out what's broken and has caused that change that created the customer complaint. Don't worry, you'll have plenty of chance to practice Ohm's law when you get into the electrical classes. Circuits. These are elements that we need when we work with electricity. Circuits can work with a power source, a conductor, and a load. They must also have a circuit control. Circuits are formed when electrons are able to flow along a path between two given points. As you see in the illustration below, we have a bulb, and that bulb will light up because there's a continuous path from the negative terminal through the ground, back to the bulb, to the positive terminal. So there is a complete path to flow from negative to positive. That is a complete circuit. Series circuits are the simplest circuit. They provide one path for current to travel. A defect in any part of the circuit will affect the entire circuit. These are generally not used in automotive applications. Very few true series circuits are used in vehicles today. This is an example of a simple series circuit. A is a switch, B is a fuse for circuit protection, and C is a lamp. When I close the switch, the electrons flow from the positive terminal through the switch, through the fuse, through the lamp bulb, and back to the ground. A complete circuit. There's also something called parallel circuits. These provide more than one path to ground. They're common in automotive applications. If one fails, it does not affect the entire circuit. This is a case where if I have a right headlight and a left headlight, if one fails, the other stays on. So this is an example of a parallel circuit where we have two paths for the electricity to follow that are independent of each other. Third circuit that you're going to deal with is what we call a series parallel circuit. This is used in automotive applications, and we'll find it in various different ways. But basically, we have two loads and two separate circuits here, which are parallel, and we have another load on a third circuit over here, which is series to those two. So this is an example of a series parallel circuit. You'll be spending weeks on these circuits and trying to diagram them and diagnose them once you get into the actual electrical classes. But just to get an idea of what the three types of circuits are: series, parallel, and series parallel. At this time, I'm going to stop